Okay, today we're going to journey into a hidden world. It's one that's all around us, all the time, and it governs everything from how you clean your clothes to the air we all breathe. We're talking about the world of surfaces, and its secrets are hiding in plain sight.
So think about something simple, like a water filter. You pour some cloudy water on one end, and perfectly clear water comes out the other. It feels like magic, right? Something incredible is happening inside with that little piece of charcoal. But what is it?
And what about soap? I mean, we all know oil and water absolutely do not mix. So how does a simple bar of soap convince that greasy dirt to just let go of your hands and wash away with plain old water?
Now, let's think even bigger. A gas mask that can save a life, a giant factory that makes fertilizer for all our food, and even the reason the sky is blue? I know, they sound completely unrelated, but believe it or not, they all share one fundamental secret.
The answer to all of these puzzles is surface chemistry. See, it's not about what things are on the inside, but about what happens right at the boundary, the interface, where one thing meets another. This is where all the action happens.
So to really understand all this, we have to start with the most basic interaction a surface can have. We can call it the sticking principle, but the scientific term is adsorption.
Okay, so here's the absolute crucial point you need to get. Adsorption is a surface-only deal. The molecules are attracted to and held on the surface of a material, kind of like posters on a wall. They don't soak deep inside.
Now this slide right here is perfect because it clears up a super common mix-up. Just picture dipping a piece of chalk into some ink. The colored dye particles, they adsorb. They stick right to the outer surface. But the liquid part of the ink, the solvent, it absorbs. It soaks deep into the chalk. So if you snapped that chalk stick in half, the outside would be colored, but the inside would just be wet. See? That's the difference.
Now, not all sticking is created equal. A surface can grab onto molecules with either a really gentle, temporary grip, or it can form a powerful, almost permanent bond, like superglue.
And this table just lays it out brilliantly. On the left, you've got fissorption. That's our weak grip. It's driven by these faint, temporary attractions, kind of like static cling, which is why it's reversible and not very picky. But then on the right, you have chemosorption. That's the superglue. It involves making actual chemical bonds, which is why it's super specific and usually permanent. And check out the enthalpy. That's why it releases so much more heat. A really strong bond is being formed.
Okay, so now let's see how this whole sticking principle builds into something even more powerful, catalysis. If adsorption is all about getting molecules to the surface, catalysis is about what happens once they're actually there.
I absolutely love this analogy. A catalyst is basically a chemical matchmaker. It provides the perfect surface where reactant molecules, which might otherwise just float on past each other, are brought close together in just the right orientation to react. And just like a good matchmaker, the catalyst itself isn't changed by the whole affair.
And here's how it actually works. It's kind of like a five-step dance. First, the reactants arrive. Then, they adsorb, or stick, onto the surface. Third, the reaction happens right there. Fourth, the new product desorbs. It lets go. And finally, it moves away. Now, this last step is so critical because it frees up that spot on the catalyst's surface to do it all over again, millions and millions of times a second.
All right, for our final principle, let's go all the way back to our soap question. This gets us into the science of colloids, or how surfaces help us mix things that nature says should absolutely not mix.
So, to get this, we need to meet the hero of our story, the soap molecule. It's this remarkable little thing with a total split personality. It's got a head that loves water, we call that hydrophilic, and then it's got this long tail that hates water but loves oil and grease, that's hydrophobic. So when you wash your hands, this is the microscopic drama that's unfolding. The soap molecules literally swarm the droplet of grease. Their oil-loving tails dive right into the grease, burying themselves inside. This leaves all the water-loving heads facing outwards, forming a perfect little sphere around the grease, a structure we call a micelle. And just like that, the grease is trapped inside a water-friendly bubble that the water can just grab onto and wash right away. And that is the whole essence of a colloid. You see, you haven't actually dissolved the grease in the water. You've just broken it up and dispersed it as tiny trapped particles. This whole system of one substance being finely dispersed in another, that's what we call a colloid. So we've seen sticking, matchmaking, and mixing.
adsorption, catalysis, and colloids. Now let's pull back and connect all of this to the world around us.
In nature, surface chemistry is literally everywhere. The blue color of the sky? Well, that's just light scattering off of colloidal dust and water particles. The formation of those massive river deltas? That happens when clay colloids in river water hit the salty ocean water and clump together. Even rain itself depends on these principles.
And industry. Wow, it would grind to a halt without surface chemistry. The Haber process uses an iron catalyst to make the ammonia for pretty much all of the world's fertilizer. The paints, the plastics, the rubber that build our modern world, they are all complex colloid systems, carefully stabilized using this science.
And in your daily life, it's just inescapable. A lot of medicines are actually colloids, so their huge surface area helps your body absorb them faster. The milk in your coffee, the butter on your toast, the ice cream you eat, they're all emulsions, which is a type of colloid. Surface chemistry is truly the science of the everyday.
So from those opening questions about charcoal filters and soap, we can now see the connecting thread, can't we? It's this powerful, hidden science that happens right at the boundary where things meet. Turns out, the secret world of surfaces isn't really secret at all. It's right in front of us and inside of us, all the time.
It really makes you wonder, doesn't it? If the simple act of two things touching can create such complex and vital things, what other invisible forces are out there shaping the world around you, just waiting to be explained?